Welcome. This is I am on the LD steel making, and today I'll discuss about the evolution of impurities in steel as well as the slag constituents during LD processing. So, the concept that will be covered, I will talk about the evolution of impurity during LD steel making, and I will also talk about the evolution of the slag and various slag practices during LD steel making. Okay, for treating different hot metal, you require different slag practices, so that we will also discuss. First is the evolution of impurities in liquid steel. So, you can see that is the with the blowing time. Here the blowing time is given in the x-axis. Blowing time is given as the percentage of total blowing time. Actually, the blowing time is around 20 minutes. So, it is the 20% of the blowing time, 40%, 60%, 80%, 100% blowing time, right. So, here it is given the percentage of the blowing time in this axis, and y-axis is percentage of impurities. So, now and phosphorus is given separately on this axis because it varies from basically 0.1 to 0.2, and other impurities is little high because the carbon is 4%, static carbon percentage is more than 4%, and your phosphorus is around, here it is depending on, that is it is little higher actually, more than 1% phosphorus was there initially. So, it is not some composition is given and typical composition, and you can find how the different impurities changes in the hot metal with time. Right, this is the phosphorus percent, right, 0.1 to 0.2% phosphorus, because it is not, right, that I was thinking, right. So, you can see the carbon percentage starts in the hot metal around 4.3, so here it is, and then your manganese and silicon both are less than 1 but near to 1, okay. And here you can find, since the phosphorus percent is 0.1, 0.2 here, so it starts less than 0.2 here, okay. So, it is a medium, there is the medium category hot metal containing phosphorus around of the order of 0.2. The phosphorus can be very high, but in Indian steel, in iron, liquid iron, the phosphorus percentage is around 0.2, 0.3 like that, okay. Anyway, so this shows the typical evolution of the impurity. You can find that carbon decreases rapidly because it is the 4.3% very high carbon. So, it decreases rapidly and finally it diminish here around 100%. So, what you can find is that there is the fastest, that is the silicon depletes the fastest. This is the silicon. Silicon depletes fastest because, as you know, silicon is the most stable oxide, and its potential for formation of the silicon oxide is very high. The gradient, potential gradient for formation of silicon oxide is very high because it is a very stable oxide, and delta G naught standard free energy change for formation of the silica is very low, okay. So, that means this delta G naught is negative, more negative, that is the, and it is a very stable oxide. So, that I was telling, that is the potential gradient for formation of the silica among all other impurities is the maximum. As a result, also kinetically also it depletes very fast. So, silicon depletes fastest. So, you can see within 20% of blowing time, silicon goes down to 0 value almost. But as we have shown you, that is the silicon during the steel making. In fact, by thermodynamic calculation, we have shown that silicon can be reduced less than 1 ppm into the steel under basic steel making condition, but because of kinetic limitation, the silicon you can reduce to around 30 to 50 ppm, that means 0.005 or 0.03. So, this is not exactly 0. So, you can see it is 0.005 or 0.03, but you can see there is the silicon can be removed to the maximum extent within the first 20% of the blowing time. And the manganese, what you can find, it decreases initially, and at the latter stage of blowing, there is a reversion of manganese, as we have discussed already in detail, because manganese among the impurity, manganese is an unique impurity in the steel in the sense that it produces an oxide that is basic in nature. The manganese oxide is basic oxide. So, when the basic slag forms, the manganese oxide do not become comfortable into the slag, and because they feel, it feels the repulsion, right. and in thermodynamic words we can say its activity coefficient increases. For the same concentration of manganese into the slag, when the basicity increases, its activity coefficient increases. As a result, its activity increases at the same concentration level. So, if the activity suddenly increases, obviously the manganese oxide will decompose to manganese again, will be reduced to manganese again because of high activity. The reverse reaction, there is the reaction Mn plus O2 forming MnO. So, the reverse reaction will take place. So, you can have some manganese reversion that is taking place. So manganese from the slag gets back to the metal phase. As a result, the manganese in the metal phase increases. So, you can find there is an hump, that is manganese is increasing in the metal phase. And at the later stage, as you will see, when the oxidation potential of the slag increases, because at the later stage when the impurity become very low, then with the blowing there is the FeO builds up again into the slag. So, oxidation potential increases, and then again because of oxidation potential increase, that is the MnO, you can see that thing. This is the reaction. I can just write it if you that is your FeO, you can write that is the FeO plus, right, Mn is equal to MnO plus Fe. So, if the activity of MnO increases because of basic slag, activity increases. So, this reaction move in the backward direction. Again, when this FeO increases, this reaction moves in the forward direction. So, if MnO increases, if you increase the MnO, activity of MnO increases, then this reaction move in this direction, right. So, the reversion, but at the later stage when the FeO again increases, then again this reaction move in the backward. So, under basic slag condition it moves in the backward direction, and at the later stage when the FeO in the slag increases, it moves again in the forward direction. So, that happens. So, that was till this the manganese passes through a hump due to its reversion, okay, when the basic slag forms. So, when the basic slag form, because the CO initially does not dissolve, because CO requires some amount of the FeO in the slag as well as little higher temperature. So, when the after some blowing period, when the FeO in the bath increases as well as the temperature, then basically basic slag form. Basic slag form basically after some time, after 40% of blowing period, the basic slag forms. And when basic slag form, then manganese is not comfortable and reverts back to the metal phase. As a result, manganese in the metal phase again increases, and at the end, when the impurity load is less, when the FeO in the slag again increases, then again it decreases because of this thing. And you can see significant dephosphorylation starts at the latter stage. Initially also you can find that phosphorus decreases, and as the temperature increases, the phosphorus reversion also takes place. Little bit in the blowing period, you can find some phosphorus reversion is there, but when the basic slag forms, then again the phosphorus reversion moves in the forward direction, because the activity of P2O5 decreases significantly under basic slag condition, as we have discussed. As a result, the phosphorus goes down very so. But so that is the significant dephosphorylation start at the latter stage when the basic slag form and continues to the end of decarbonization. The aim is that the dephosphorylation should end before the decarbonization, because as the decarbonization ends, the emulsion will collapse. As a result, your refining kinetics will be very low. So, aim is there that till the phosphorus is not completely removed from the liquid iron, that is you have to, there is the carbon should be preserved till the end, such that decarbonation continues and the emulsion is stable, such that you can remove the phosphorus most effectively. Otherwise, if the emulsion collapses before the complete phosphorus removal, the rest of the phosphorus cannot be removed easily. Okay. So, it is difficult. So, that thing, the aim is to finish that. So, you can find here there is a decarbon and the phosphorus removed simultaneously till the end, right. Okay. So, this is the impurity evolution. Now, let us see the evolution of the slag constituents. As you can find, that is the FeO initially increases and attains a maximum. Why initially FeO increases? Because initially it is the series, because initially you have, when you are charging the oxygen, so oxygen sees only the iron, so iron oxide forms, and then the impurity slowly is transported from the bulk to the slag metal interface and it consumes the FeO. So, initially what is removed? Only the silica is removed. Initially you can find in the slag the silica is increasing initially little bit. This is the only impurity load, because the phosphorus removal do not take place till the basic slag form, and it forms after some blowing period. Okay. So, only load in the initial period is the silicon and manganese, right. Silicon and manganese is the only load, and silicon is the, so only the Fu is consumed by the silicon and manganese to some extent. Okay. So, Fu, that is the load on Fu is not high, that is the rate of formation of Fu initially is much higher compared to rate of its consumption for oxidation of silicon and manganese. So, Fu basically gradually increases during this period, it makes. And after that what happens, as the time progresses, when Fu is sufficient into the slag and temperature also high in the slag, then CO start dissolving. You can find that the CO appears here. So, CO in the slag, CO starts dissolving and it appears into the slag, and finally you can see there is the slag, the CO percentage is increases in the slag, like this. It is increasing, and rapidly it is increasing after some time. When the basics, that is the after some time, that is the CO start dissolving and it increases. And then FO decreases only because of dilution effect, that is the CO increases into the slag because of dilution, FO basically decreases. And also FO decreases, another reason is that at that point when the basic slag form, then the P2 phosphorus also start oxidizing, right, and it is transferring to the slag phase. So, the impurity load is maximum, plus because of dilution effect, two effect, that is the FO goes down, FO percentage in the slag decreases very much. And then you can find, and after some time again it increases, because again it increases due to the fact that lime dissolution stops after some time, and also dilution effect gone, and also your impurity load is also less at the end of the blowing period. So, then whatever your oxygen charging, it is the Fe amount, the rate of formation of Fe become much greater than whatever it is consumed by the impurity, because impurity loss is very less. So, Fe again start increasing in this position. Okay. So, Fe, that is why Fe curve moves like this, and CO this, and MnO obviously because of dilution it goes down, and silica initially increases and then goes down because of dilution, because dilution continues for silica, because now here the calcium oxide was increasing and here the Fu is increasing. So, because of dilution COMnO decreases, right. So, that is the thing I have said, that is the Fu in the slag increases initially due to more generation of Fu compared to the reduction by the impurity oxidation, and decreases later due to dilution by CO, and at the end Fu increases again due to the reduced impurity load, right. And the CO requires Fu and temperature to dissolve. So, CO does not instantly doesn't get dissolved, then the CO appears in the slag after some time of blowing and thereafter dissolve very fast. You can see it fastly increases. Okay. So, this is typical, that is the evolution of the slag. Now, I will discuss about, so you can see here, that is the when the Fu increases the latter stage, so manganese also, when the oxidation potential of the slag increases, then manganese again goes to the slag phase, because that reaction, that is that reaction. You can see there is at the latter stage the oxidation potential of the slag increases. Okay. So, now I will discuss about the slag practices, and first is the heat one, that is the Hugomans plant, and this slag practice is basically, it is the treatment of high carbon and the low phosphorus hot metal. So, what we do here basically, low phosphorus means that is the when the phosphorus percentage is say less than 0.1%. Okay, less than 0.1%, that is in Indian steel we have phosphorus percentage from 0.1 to 0.4 in this range somewhere, and some very high phosphorus steel is also there in the European countries where the phosphorus percentage may be even greater than 1%. So, here what we are talking about, this is a very low, and this Japanese there is the hot metal is also contain lot of low phosphorus hot metal, right. So, low phosphorus hot metal means when the percentage of phosphorus is less than say 0.1 and the carbon percentage obviously it is greater than 4, right. So, we have lot of carbon into the hot metal, but we have a phosphorus very low, limited amount. So, what I have to do in this case, what type of slag practice I have to evolve, that is from the beginning I have to target to remove the carbon. that is the carbon has to be eliminated from the beginning. Okay. And when at the latter stage, because we don't have to preserve the carbon here, because large amount of carbon is there. Rather, we should be concerned about removing the carbon within this blowing period, right? So, from the beginning, we'll keep an eye on the high decarbonization rate, and when during the process, when the basic slag form after some time, then the phosphorus removal will start, and it will not take too much of time, right? Because only 0.1%, less than 0.1% phosphorus, if you want to remove it, it will not take too much of time. So, it will be removed under basic slag condition and with decarbonization, and even after when the phosphorus will be removed, then your decarbonization will continue. So, this is the idea. So, because my concern here, it is not removing the phosphorus. Phosphorus is so low, when the basic slag form, it will be removed in a very small time. My concern is how to remove the very carbon within this blowing period. So, my concern is here from the beginning, we have to remove the carbon at a higher rate. So, what is this? This is the slag 1 practice. This is you can find, that is this is the heat 1, that is the slag 1. This is the way the slag has been evolved with time. Okay. So, what we did here is that initially you can find, that is the percentage of iron. If you see this line, parallel line to this, if you have this line, you have this is the line, right? This is the iron line. So, iron line basically it increases, you can see these are the parallel lines, right. So, as you go in this direction, you can find that is the iron percentage is in this direction, that is the iron is increasing in this direction. This is not correct thing. So, this is the FeO percentage is increases in this direction, right. FeO percentage is increase in this direction. So, you can find that is as I am moving from here to here, my iron percentage is decreasing. Here is the maximum iron. So, we are starting with a very high amount of FeO. How we can do that? We can achieve it by adding some amount of the mill scale. Okay, that is the only thing, the mill scale. So, from the beginning, we can start with a large amount of FeO, that is we can add some mill scale. So, if you add the mill scale, then the FeO percentage is very high. So, you can start decarbonization from the beginning at a very high rate. And as the process is going, you can find that is as the blowing process continues, then temperature will increase. FeO is already there in the slag. So, lime will start dissolving after some time when the temperature in the slag increases, and then lime also will start dissolving. Okay. So, you can find with the progress of the process, that is the decarbonization is going on, that is why your FeO is going down. But although the FeO is always forming, but because of decarbonization, there is the FeO percentage is decreasing. And you can see the calcium percentage also increasing with time. If you see, the calcium line will be this line, these parallel lines are the calcium line. So, initially maybe, sorry, I will change this red line. Okay. So, where it is not changing, 1 minute. Okay, fine, it is not changing at all. Fine. So, this is your this is the CO line, that is the CO is increasing in this way. So, CO is increasing by this line, and FeO is increasing in this or decreasing in this way. Okay. So, CO you can find with as the process goes on, there is the CO percentage in the slag increases and your FeO percentage decreases. FeO percentage decreases and the stress, there is the FeO decreases and the CO is increasing. So, basic slag is forming. Suppose your basic slag is formed somewhere here. So, somewhere here your basic slag has formed, and then the dephosphorylation will start here, and it will continue because very small amount of phosphorus, maybe it will finish by this time. There is a dephosphorylation will be completed during this period, because when the basic slag form and the dephosphorylation starts, and it will complete within very short time, and after that only the decarbonization will continue, and finally it will come here, right. So, because as the carbon load is decreasing, again you can find that is the FeO in the slag start increasing here, So, that is the way it will be done. So, this type of treating this slag is not at all difficult, because So here the intention is to remove the carbon at a faster rate from the beginning, because when dephosphorylation catch up at the latter stage with basic slag, it does not require much time, but decarbonation needs to be completed during this flow. That's what I wanted to say here. So the slag, that I say that the slag starts with the large FU here at this point. To do that, as I said, you add some mill scale, and the decarbonation starts from the beginning at moderate rate, and dephosphorylation joins later when basic slag formed, and it also completes within a very short period of time and then decreases. So this slag practice is okay. That is very standard slag practice. When you have a low phosphorus, it is not at all a problem. We should not be concerned about the preserving the carbon, okay, because carbon is already very high and the phosphorus is very low, okay. So now we go to the next slag practice, that is the heat to management plant, because here you have for treatment of German that is your hot metal contains little higher phosphorus. So it is a high phosphorus hot metal. For treatment of high phosphorus hot metal, there is a management plug in Germany. So there they have the high phosphorus hot metal. So phosphorus is quite high, maybe of the order of 1% phosphorus. Okay. Then what type of slag? And then carbon is in 4% only, and the phosphorus. Previous case it was 0.1, now maybe it is 0.1%, 1% or more than that, right? Very high phosphorus, and carbon is 4%. So in this case, when the phosphorus is very high, then you have to be very economic in consuming the carbon from the beginning of the heat. So you can find, now I will follow this type of slag evolution. This is the slag evolution. So when we start, then I have the FU is very less here. When I am starting, this is the FU. At the start, the FU is this. At the starting point, I have say this much of FU. So here I have, so we are starting with this much of FU. This is the FU. Okay, it is around 25% in the phosphorus, and this is basically what we are doing in this case. Why in the beginning the phosphorus, the iron oxide is high. Here we start with the process where I need the FU, but I should here my intention is to develop a slag with basic slag without consuming much of the carbon. So my intention is to not to remove the carbon from the system, but I want to, or you can say with minimal removal of the carbon, I want to develop a basic slag very quickly. So I want to develop a basic slag with minimal of carbon consumption in the bath. So we start with 25% of FU. Now how we can do that thing? Basically we can develop this by soft blowing. If I do a soft blow, then the very soft blow, then in that case I can develop the FU in the slag at the same time without losing the carbon. That is, the decarbonation rate will be very less at a soft blowing, only the FU will develop, right. So, and if I can, so with minimal removal of the carbon, I want to develop the basic slag, that is the thing. So we start with little less FU. You can see here we started with very high FU because I wanted to start the decarbonation at a very high level. Here what we will do, basically we will start with a very soft blow such that the FU forms and without sacrificing much of the carbon. And so at that period, that is when some amount of blow has done, some amount of impurity oxidation has taken place like silica and all this. So as a result, the heat will be evolved. And then since I have already at the starting we have a 25% FU is there, only some temperature is needed for calcium oxide to dissolve. So I have to blow for some time, a soft blow, such that I can develop the temperature in the bath. FU is already there, and then some FU will be added also, and then CO will start dissolve. So I want to form a basic slag without much sacrificing the carbon into the bath. That is my intention. So we start with this type of FU, and then you can see, and then what is the, you can see that is what is the percentage of, this is the percentage of CO, maybe around 40%. So you can find here That is, after soft blowing we have come to a position that we are starting at this position without doing much of decarburization. So, you have 40% CO. So, CO has already dissolved. So, if we start with certain amount of the FeO, say mill scale, small or we can start with the just soft blowing, and after some time we can evolve a basic slag very quickly. So, again what it is going on there, and then you are moving in this direction. When you are moving in this direction, what you are doing basically, when you come here and you have an, sorry, same thing if I can use some other line for iron oxide. Yeah, it is coming. So, this is the iron oxide line, say this is the iron oxide. So, now FeO was there 20, here you can find there is the FeO is very high, because we have done a significant soft blow. So, lot of FeO has formed, and you can see here your basic oxide was like this, and then yeah, soft blow period, and then you soft blow, basically you are evolving, that is the evolving the FeO in the slag, and then what is happening is the slag is moving in this direction. That means your this percentage is increasing, your what is that called, that is your this percentage, that is the CO percentage is increasing now, progressively increasing. You can say this way, you can say this way, your CO is increasing. So, up to this we have done, we started with 25% FeO, and then we have done a soft blow, and then FeO I am evolving, and I have developed FeO very high, 40% without losing too much of carbon, and then you can see the CO start dissolving, and then CO is increasing into the slag, CO is increasing. So, I have formed the basic slag in this condition, that is the significant basic slag is there, right, yeah. So, this the basic slag is there, and then your phosphorus removal will take place, and this for all this region, that is this region, this is the region where the dephosphorylation will take place. When the basic slag form, the dephosphorylation will take place, decarburization, and also the decarburization will continue simultaneously, and finally you will be able to do that. So, thing is that here, so soft blowing initially to build up the FeO and temperature for early formation of the basic slag without losing much of carbon, that is the intention. So, we are doing the soft blowing here. So, only we are increasing the FeO percentage, right, without losing the carbon. And then when it is moving in this direction, that means the CO start dissolving, and you have formed a basic slag, and in this region basically here your dephosphorylation and decarburization will continue simultaneously. And my aim is to complete the dephosphorylation before decarburization, such that I can remove all the phosphorus as long as emulsion is stable, right, yeah. So, that is the only thing that we do. So, then dephosphorylation, decarburization continues simultaneously till the end, right. So, this is the two slag practice. One is if you have a very small amount of phosphorus, or if you have a very high amount of phosphorus. The high amount of phosphorus, then only you are concerned, and you have to preserve the carbon till the end. So, in that case, initially you start with the soft blow, such that you can develop a basic slag without sacrificing too much of carbon, and then early formation of basic slag, you try to form the basic slag very fast. So, initially we started with some amount of iron oxide already. So, you can add some amount of iron oxide at the beginning, and then do a soft blowing, such that you can develop some temperature, because you have lot of FeO now. So, you can form the early basic slag. I want to form the basic slag. So, basic slag formation, thing is that CO only dissolve into the slag when you have significant amount of the FeO and temperature. These two things are important. So, we have started with little more, that is the some FeO, not too high FeO. Then if FeO is very high, the decarburization will from the beginning will start at a very high rate. So, we give some amount of FeO, 20% mill scale we give in the slag, 20% FeO is there. And then we give a soft blow, such that we can bring the iron oxide. So, after the end of that is the end of soft blow, iron oxide is 40%, and then CO also start dissolving at that point, because you have a temperature and FeO. So, a very early dissolution of the CO take place, and then you start dephosphorylation, and decarburization ends continuously till the end. Okay. So, these are the basically E.T. Towdogan, Fundamental of Steel Making. You can go through this book, Ghosh Chatterjee, and this book is also important. Okay. So now the conclusion you can say that is that during the refining of liquid iron, silicon depletes first, and then manganese also reversion take place when the basic slag forms, and in slag FU builds up initially and then decreases due to the CO dilution, and finally again increases because of lower impurity load, and the CO start dissolving when FU builds up in the slag, as well as the slag has some temperature. Okay, so after some initial blow, you can have the FU build up and temperature, and then the CO start dissolving, and thereafter it dissolves very fast rate. And dephosphorylation starts only when the basic slags form after some initial blow, right. And for treating the high phosphorus hot metal, this is more important. Treating the low phosphorus hot metal is not at all a problem. Okay, rather in that case you start with a very large amount of the FU in the bath, that is you can add some amount of mill scale if you want, and then phosphorus, when the basic slag form, phosphorus will be removed, less amount of phosphorus. But if you have a very high phosphorus, so you have to be concerned about preserving the carbon till the end of the process, and for that you do the soft blow, develop the FU in the slag, and early form the basic slag such that the dephosphorylation starts little early, and then you continue dephosphorylation, decarburization simultaneously. Okay. Thank you in this lecture.